So, hi. My name is Lior Ben Gai. I'm a computational artist and designer. And I always get nervous during the first kind of minute of the conversation, so we're going to spend it playing a little game. One of these things is very, very small, and the other one is very, very big. In other words, one was taken with a microscope, and the other one with a satellite. Can you kind of tell which is which? Microscope, this one? How about this one? Who says microscope is left one? Not a lot of agreement. How about now? Microscope, satellite? Microscope?
Yes.
Last one, surprise one. Microscope, satellite. Right, so, I mean, as an artist and as a programmer, I've always been quite, I guess, inspired by this question of why things around us converge to certain forms and not others. And so today I'm going to tell you a little bit about how I explored virtual phenomena with these ideas in mind. And so as a master's student, I kind of quickly became familiar with a field called artificial life. And basically saying, life as it could be, right? So it alludes to this idea that biology could be the study of much more than the things that we see around us, right? That there's like a massive field of possible phenomena, and we only get exposed to this tiny fraction of what's possible. And specifically, Langton and many others in the field, they used programming as a means to explore what else could there be. So for the better part of a year as a master's student, I started using algorithms that are usually associated with biological phenomena and maybe used by scientists, but I used them in a way that was maybe more abstract. I wasn't concerned with simulating existing phenomena, but much more in just exploring abstract structures. And yeah, I'll kind of, much to see. So just for example, if we talk about something like flocking or swarming, so this is a good example of a complex system. It's a system of interacting components, and its attributes are fueled by the interactions between these constituent parts, leading to complex global behavior. But this behavior can be studied and implemented using algorithms. And so you might start off with something quite similar to the original subject matter, but then maybe you can start to just slowly steer away from it and just consider it as if it were dots and lines, but that produce interesting structures regardless of the original subject matter. And so you can start exploring just in the parameter space, right? You can tweak the algorithm to kind of get a sense of what else, what kind of behaviors you can achieve with it. Still nervous, 2 minutes and counting. And so I started moving further and further away from physical phenomena and just explored this space of just abstract computer programs. And it leads to quite interesting artifacts and structures and morphologies. And you can still deal with things like scale and the feeling of, I don't know, it's hard to express. At a certain point, I got to study something, I guess you could describe it as a sort of magnetic self-assembly. And it started producing really interesting results. I kind of knew I struck something when I caught a look at this guy. Right? You could see it right there. This is a very simple computer program. It's, I guess, maybe not more than 5 lines of code, and it describes how a system of interacting parts can assemble, the rules in which they can assemble and then maybe disassemble. And interesting things started happening. And it really became this quest of exploration where each night I would just kind of set a few parameters different from the previous night and then go to sleep. It would take it hours to sort of get to something and then wake up in the morning to see what sort of things emerge from this computer program. like with really interesting strategies for locomotion and persistence, and really started feeling like I was looking in this petri dish of things. And every time you tweak a few parameters, you get something else. This is a time lapse of like a massive structure that for some reason stopped working, but all of its parts reassemble and kind of compose into new things that then wander off to better horizons, and tweak the program maybe a bit more, and you'd see these mega structures with tentacles reaching out to assimilate new members. I'm just gonna let it simmer for a second. This is another time lapse of these two mega structures who happen to be close enough to kind of decide to converge and become this larger thing. All right, so a different type of algorithm, which I kind of experimented with, is called Cellular Automata. And this algorithm was immensely interesting to me because, again, minuscule programs, just one line of code, and suddenly you get this massive city of structures and pipes with things going through them. And I just found it mind-blowing. So mind-blowing, in fact, that I decided to do a PhD about this topic. Something which I'm betting a lot of PhDs in the room would agree is a terrible, terrible idea. Just to kind of, 2 words on cellular automata. If we think of static images, these images we see around us, like with a camera, each pixel has a constant value, and that's the color of the pixel. But in cellular automata, each pixel looks at its adjacent neighbors and then decides, oh, these guys are this color, so I'm going to be something else. And this is performed by all pixels all of the time. Again, a system of interacting components. And that leads to complex dynamics and feedback between them. So maybe some of you know one of the most widely known cellular automata algorithms is Conway's game of life. And it became quite famous, and rightly so, because it has really interesting structures emerging from really, really simple rules. So my approach to exploration was to use a version of these algorithms which you could say maybe much more of a mathematical version of algorithms, not to write them as general purpose languages, but something much more algebraic. And the advantage is that once you do that, you can change any operator or parameter and you're getting something else. Maybe interesting, usually not, but something else nonetheless. And so this approach enabled me to start having many, many variations of widely known algorithms. And so this is just one of many variations to Conway's game of life that I've been able to uncover. So I started exploring. I started making my own tools, initially quite simple ones. Also experimented with representations of these algorithms. This is quite a minimal one. I ultimately abandoned this one. And started progressing with tools that are specifically designed for exploration of cellular automata algorithms. In a more kind of later representation, I was able to represent these algorithms as I guess you can see it, a kind of visual representation. And I think this kind of shows that any change you give to the system, even just of a single parameter, you're getting potentially massively different results. And it starts to feel less like exploring, less like programming, and more as if navigating this vast field of possible phenomena. And again, complex phenomena that's very hard or sometimes impossible to predict, essentially containing things that no one's ever seen before. I still find this immensely exciting. Also experimented a bit with 3D cellular automata. Didn't go that well, I have to admit, but the tools became more and more advanced, I guess. I kept progressing with the tools themselves. Here is an earlier version of my programming environment that enables me to start creating random cellular automata algorithms. And I think it's easy to see that, and it is a fact that most of them are just really, really useless. But every now and again, you come across something, and then maybe you can extract more interesting behavior out of that something. And this kind of alludes to this idea that there is a space, a massive, massive space of possible cellular automata algorithms. And it reminded me of a story, the Library of Babel, this kind of famous story about a library containing all possible books of a given format. And it's kind of grim, but worth a read. Also, I recommend libraryofbabel.info, a wonderful online implementation of this kind of paradoxical space. So my project would become the laboratory of Babel, which would be the space of all possible cellular automata algorithms. Oh, we're with time? Okay, much to see. So if to summarize my research, it would go something like this. There are countless possible cellular automata algorithms. Almost all of them are completely useless. Let's explore them anyway. Here are some methods. And so by now, my programming environment, Automata, it's, by the way, an online programming environment, which you're free to explore as well if you want. It became quite a robust tool for research that enabled me to start gathering, collecting, and experimenting with different cellular automata algorithms. And by now, this feeling of not really being a programmer sort of feels more like a farmer, because you're just cropping fields of possible behaviors and selecting between them. And so it would go something a bit like this. You'd find some behavior that I find interesting, and then you get a field of kind of sibling behaviors, things that are somewhat mathematically like that behavior, but slightly different. And then you start exploring some variation of that behavior. And that's interesting as well. This one's colorful, right? And then something, near that, you suddenly see these, I don't know, like, this abundance of new phenomena to explore. And each new behavior like this comes with its own kind of ways of structuring and these weird organisms, which in themselves are worthy of, a complete taxonomical research. And maybe go a little to the left and kind of they're cousins, and they're similar, but also quite different with their own properties, and et cetera, et cetera. It becomes quite Sisyphic at a certain point. Yeah. So here we are with something, some of them really in kind of professionalism aside, I just found them really engaging, and this feeling of who knows what else is out there in these vast virtual domains. I just found it really exciting. By now, algorithms, I've become so far removed from the algorithm itself. I have obviously no analytical understanding of what these algorithms mean, but I can generate them, and they act as this sort of genetic code of virtual phenomena. And so I've also experimented with evolving them kind of explicitly using interactive evolutionary algorithms. So I'll finish with my latest discovery, a family of algorithms which I call type U. They start off with just random pixels, but they start sorting themselves out into interesting structures. And they're an immensely large family of algorithms with trillions and trillions of instances, but each one, kind of unique, and they all still share this aesthetic and types of behavior in common. Some of them are more kind of, organic and wild, I guess, and others might have really large-scale structures emerging from them. And again, this idea of archiving them and having a taxonomy of possible structures with these machines that kind of just emerge from nothing, from pure randomness, maybe not pure, but definitely randomness. So I kind of thought about how to conclude this project and this lecture, and to be honest, it doesn't conclude. It's a work in progress, and if I'll be lucky, I'll get to keep exploring it, and I think maybe that's a good message in itself. I wanted to show you, just because I'm in this segment about mapping, the latest software that I've been working on, which is, oh, it crashed. No. Well, maybe I won't show you it. Come on, you can do it. You can do it. Yes, you can do it. It's happening. Let's do it this way, and this way, and this way. Right. So again, a piece of software designed to explore this particular family of algorithms, but in a vast space which we can, navigate around. And every two instances are actually neighbors. They only differ in one operator or parameter from each other. And we can just kind of move around this massive space randomly. And the point is that we really don't know what's out there. There are trillions and trillions just of versions of this particular family. It's really hard to say, and so I'm going to keep exploring. I'll let you know how it goes in the future. Thank you.